Hello everyone, today we'll discuss work and energy part 1. So let's start defining work. So work done by constant force is defined as work equal to F dot delta R, or magnitude of F, magnitude of delta R cosine theta, and theta is the angle between the displacement delta R and the force F. Based on this definition right here, this one here, work is scalar quantity with joule units, and sometimes it's like this. Since the work is scalar quantity, then the total work is just adding work together. So the total work here is the work done by all forces on the system. So it's work 1 plus work 2 plus work n, or F net dot delta R. So work total equal sum of all forces dot delta R. Therefore work total equal to F net dot delta R. In other words, if you want to define the work total or the total work on the whole system, you can just find the net force and dot product with the displacement. In this model, we have a block placed on flat, frictionless surface like this one here. As we can see here, we have here the normal force, this one here, the normal force, and the weight of the object is downward like this one here. If we provide a horizontal driving force with 1 Newton, in this case here, the driving force is directed this way here. The driving force is directed this way here. So this is F. And the displacement, again in this one here, is directed this way here. So both displacement, in this case it's not delta R, it's delta X, since it's in one dimension, and in the X direction. In this case here, the work done by this force F equal to F dot delta X. Now, the total work, in this case here, equal to work done by all forces on the system. In this case, we have gravity and work done by the gravity, work done by the normal force, and work done by the force F. Now, as another model for this one here, the driving force for this case here, it's not in the horizontal direction. The driving force is like this one here, this one here, this red one here. It's the driving force in this case. The displacement is directed this way here. Now, work done by this force equal to, by F, equal to magnitude of F, magnitude delta X, cosine theta, and theta in this case is this one here. Or we can analyze the force here as X component F cosine theta and F sine theta. So in this case, again, work done by force F here equal to magnitude of F delta X cosine theta, which is F cosine theta, the X component. And the work done by the gravity and the normal equal to 0. Even the work done by the Y component of the force F, it's equal to 0. So work done by Fy equal to 0 as well. Let's see here. So the only force acting here is the X component of the force, not all the force, just the X component of that force. Now let's have an example. In the figure, a force pulls a 50 kilogram object 40 meters along a horizontal floor by 100 Newton force. If the friction force is equal to 25 newtons, find the work done by F, find the work done by frictional force, and find the work done by normal force, work done by gravitational force, and work done by total force. So we have here flat horizontal surface, and here's the block. Now a force F directed this way here, and frictional force directed this way here. Again, this is the displacement this way here. So this is F. So this is displacement, and this is the frictional force. Theta here, it's equal to 60 degrees, and that's all. So let's identify the forces acting on this object. So we have here F, frictional force, and we have weight directed this way here, it's mg, and we have here the normal force. Now to find the work done by force F, so work by just F equal to F delta X cosine theta. And remember, theta is the angle between F and delta X. Or we can say that 100 Newton multiplied by the displacement 40 meters cosine 60, which equal to, in this case, 2000 joule. Now work done by the frictional force, it's equal to same rule, F delta X cosine phi, and this case phi is the angle between Fk and delta X. So by looking at this graph here, delta X is directed this way and Fk is directed this way. So the angle between Fk and delta X, it's 180. Cosine 180, it's equal to minus 1. In this case, the answer is 25 times 40 cosine 180, which equal to, in this case, minus 1000 joule. Work done by the normal force equal to, in this case, it's just very simple here, the angle between delta X here and the normal force equal to 90 degrees. So cosine 90 equal to 0. Same rule here, and the answer will be 0. And work done by the gravitational force, again, same explanation here, it's equal to 0 as well. Now to find the total work is the work done by force F plus the work done by frictional force in this case, which equal to 2000 plus minus 1000. This one here, the work done by the force F, and this one here is the work done by frictional force, and the answer is 1000 joule. Based on this example, we notice three things. Work could be positive, work could be negative, and work could be zero. Positive work, it means work done on the system. It means work done on the system. In this case, the work done by the external force to drag the object on horizontal surface. Now, negative work means the work done by the system, which in this case is the work done by the frictional force. Zero, it means the angle between the force and displacement equal to 90 degrees, or there's no force or no displacement. Now let's discuss work done by varying force. Work done by varying force. If the force acting on an object is dependent on the position of the object. Now let's draw a varying force with respect to position. Now to deal with this situation here, we chop this curve into small slices like this one here. The width for each slice is dx here. Now the area for this slice here equal to f dot dx. So the work done, it's in this case dw, for this small slice here equal to f dot dx. Now we need to sweep all the area here. In this case, work equal to integration f dot dx from x1 here to x2, if the curve here x1 and here x2. And by the way, this is the definition of integration. So the work done by varying force is the integration from x1 to x2 f dot dx. Or in other words, it's actually the area beneath this curve. So this is the area here. Now let's consider this case here. Example. Now in this example, calculate the work done by the force as the object moves from x equal to 0 to x equal to 4. So we need to calculate the work done from 0 to 4. As we can see here, we can divide this curve into two known areas. The first one, this one here, is the triangle, and the second one is the rectangle. Now the total work is actually equal to the work done, or the area beneath this curve here, plus the area beneath this curve here. Now this one here is triangle, so the work done in this case here equal to the area of triangle half base. In this case, base is equal to 2 minus 0, it's 2, times the height equal to, in this case, 3 times 3, which equal to 3. So the area beneath this triangle here equal to 3. Since we are calculating work, it's equal to 3 joules. Now the area beneath this curve here, it's actually a rectangle. In this case, the area of the rectangle is the width times the length. In this case, let's name it work 1. So work 2 equal to the width, in this case it's 4 minus 2, it's equal to 2 times the height, in this case it's equal to 3, in total 6 joules. So the total work, that's what we're looking for, equal to, you add 3, this one here, 3 joules plus 6 joules, 3 plus 6, which equal to 9 joules. One of the important forces we will discuss here is the spring force. So let's have here spring force. Spring force is defined as minus kx. In such a way, k is the spring constant and x is the displacement. Now k is spring constant and it has to be positive, and x is displacement. As we can see here, this force, this one here, is position dependent, and the magnitude for the spring force equal to just kx. Now in this model, as we can see here, a car is connected with a spring. Now it's given an initial velocity, and this, by the way, this is the relaxed position, x equal to, in this case, equal to 0. Now this is the maximum elongation for the spring, and this is the maximum compression for the same spring. As we can see here, the relaxed position, it's somewhere in this one here, and x in this one here equal to 0. Now the maximum elongation, x will be in this one here, maximum, and the maximum compression will be x max. So let's see here. In this case, the cart is moving back and forth, and so on. Since this is a varying force, in this case, work done by this varying force is defined as the integration from initial position to final position, F minus kx dx, or in this case here, half kx squared from x initial, x final, don't forget the minus sign. So the work done by the spring equal to, in this case here, minus half k x final square minus x initial square. But the work done by the external force here is the positive of this one here, which equal to half k x final square minus x initial square. We're actually interested in the work done by the spring, unless for some reason the external work is required. In this case, we just calculate the negative of the work done by the spring. So work done by the spring is equal to half k. You may write it like this way: x initial square minus x final square, or you can say that work done by the spring equal to half k x initial square minus half k x final square. Now this one here is called elastic potential energy. The final elastic potential energy. Let's take this example here. A 10 centimeter long spring is stretched to a length of 14 centimeter when an object of 0.5 kilogram suspended from its end. If the object is in equilibrium, find the spring constant and what is the magnitude of the spring force when it is stretched to a length of 15 centimeter. By the way, this is one of the techniques used to find a spring constant. So we have here spring, so this is the relax position, and here's the mass m. Now in this situation here, we have the weight of the object, which is directed this way here. Now let's change the color here to make it more clear. So we have here the weight of the object, and we have here the force constant. Now in this case here, sum of all forces equal to, remember Newton's second law, it's either 0 or ma. Since the question mentioned that it's in equilibrium, so there is no acceleration whatsoever. So in this case here, sum of all forces equal to 0. Forces we have here, we have mg, we have kx. Or we can say that kx in this case equal to mg, or the spring constant k equal to mg divided by the x. X here is the displacement from the relaxed position, so this is the new x here. Now x final, this one here. Now x final here, it's stretched from 10 to 14, which means k here, it means the object mass, it's 0.5 times almost 10 divided by 14 minus 10. 14 is the final position and 10 is the initial position of the spring, and in this case k here equal to 122.5 newtons per meter. Now if the spring is stretched to 15 centimeters, in this case x here, the displacement equal to 15 minus 10, or equal to 5 centimeter. In this case here, the magnitude for the spring constant equal to kx, or in this case equal to 122.5, and remember we have to convert the centimeter into meters, multiplied by 0.05, which equal to 6.125 Newton. Example: if the spring constant K equal to 2000 Newton per meter, how much work is done by the spring as the object moves from 0 to 3 centimeter? In this case here, we have here a spring, an object here, and the spring is stretched from 0 to 3 centimeter. So this x final here, and this x initial equal to 0. So in this case here, work done by this spring equal to, same rule as we mentioned before, half kx initial square minus half kx final square, and this one here equal to 0 because x initial equal to 0, this one here, and this one here equal to minus half k x final square. It's equal to 3, but we have to convert the 3 centimeter into meters. So in this case here equal to half k 0.03 square. You substitute k equal to 2000 and you calculate this, and you will get work done by the spring equal to minus 0.9 joule. Now if we look for work done on the spring, it has to be work external here equal to 0.9 joule, or work done on the spring. Example: how does the work required to stretch a spring 2 centimeter compare with the work required to stretch the same spring 1 centimeter? As we can see here, the relation between the work and the displacement is this. In this case here, if the spring stretched 2 centimeter, it means the work done by the spring is proportional with 4. Now, if the spring stretch 1 centimeter, is the work done by the same spring is proportional to 1 square, which equal to 1. In this case, the relation will be 4 times the work. So the work done by the spring, if we stretch it 1 centimeter, is the proportional to 1, while the work done by the spring, if we stretch it 2 centimeter, is proportional with 4. So the answer is 4 times the work. Now let's identify potential energy. Potential energy is defined as the energy stored in an object. Now, gravitational potential energy of an object with mass m is defined as U equal to mg y. In such a way, m is the mass of the object, g is the acceleration of gravity, and y here is the height. Now the work done by the gravitational force equal to minus delta U. In such a way, U here is the potential energy, or you can say work done by the gravity, it's equal to minus U final minus U initial. In other words, we can say that work done by the gravity, it's equal to U initial minus U final. Work done by gravity equal to mg y initial minus y final. So the gravitational potential energy depends crucially on the height of the object. Let's have an example. A mass is attached to a vertical spring, causes the spring to stretch and the mass to move downward. What can we say about the spring's potential energy and the gravitational potential energy of the mass? This example combines two cases, elastic potential energy and gravitational potential energy. Now, before answering this example, let's have this model. As we can see here in this model, an object is attached to a spring. Now, the spring stretches to a maximum displacement. It's somewhere here, this one here. So this one here, actually delta x, the displacement that the spring stretches. So the elastic potential energy of the spring will be increased because delta x is increasing. Now, on the other hand, the height of the object from the ground level, this one here, is decreasing, which means the gravitational potential energy decrease. So in other words, just in simple words, increasing the elastic potential energy will be directly followed by decreasing the gravitational potential energy. Gravitational potential energy U here in this case equal to mgy, and elastic potential energy equal to this gravitational and this Fourier spring half kx square. So increasing x will increase this one here, and increasing x will be followed by decreasing y, which means this one will be decreased as well. Let's see here. So this one here decreasing, and this one here increasing, and vice versa. So to answer this example here, let's say U for gravity equal to mgy, and U for spring elastic potential energy, it's half kx square. Increasing this will increase the elastic potential energy. Increasing this will be directly followed by decreasing y, which means this will be decreased as well. Now, or increasing this will increase the gravitational potential energy, and increasing this will be decreasing the displacement in this case here, which means the elastic potential energy will decrease. Or in other words, gravitational potential energy is oppositely correlated with the elastic potential energy. Ug here is proportional with 1 over us. Example: is it possible for gravitational potential energy of an object to be negative? The simple answer for this one is yes, because it depends on the reference point. For instance, we have an object here on a table, this one here, and this ground. So the potential energy of this object here with respect to the ground is positive, but the potential energy of this object here with respect to the ceiling of the room is negative, because here the reference point in this case here, and this one here, it's in the negative direction. So the simple answer is yes. Example: an object of mass m equal to 5 kilograms falls from height of 100 meters above the ground to a height 40 meters. Calculate the work done by gravitational force. So in this case here we have an object, let's say this one here, this object here is fall down from a height 100 meters. And at some point here, while the object height equal to 40 meters, how much the work done by gravitational force? So work done by gravitational force equal to minus delta U, or U initial minus U final. In this case, work done by gravity equal to minus mg times y final minus y initial. In other words, work done by gravity equal to minus 5 times 10 times, now y final is this one here, this one here, this is y final, and y initial is this one here. So equal to 40 minus 100, which equal to work done by gravity equal to 2940 joule. Another example, a 50 kilogram object is pulled 10 meters up along 30 degrees inclined plane. What is the work done by gravitational force on the object? So here's the situation. So we have here inclined surface like this one here, and here's the object, this one here. We pull this one like this one here, this one here. Now this is the length of the path, it's 10 meters, this one here, and this is y initial and this is y final. Now this is theta equal to 30 degrees. Now to find the work done by gravitational force, remember the equation equal to minus delta U, which means U final minus U initial with minus sign. This equation here, it means we're only interested in the initial and final position of the situation here. We are not interested in the path itself. We are really interested in the initial position here and final position, which is this one here. Assuming that the Earth is this, here's the Earth. This means y initial equal to 0 and y final, we can find y final from this right angle triangle equal to sine theta over 10, or in other words equal to y final equal to 5 meters. Now to calculate the work done by gravitational force, the work done by gravitational force equal to minus mg y final minus y initial minus 50 times 10 times y final. We just calculated this one here, it's equal to 5 meters. You substitute numbers, it's equal to minus 2450 joules. Now let's have an example. Two paths lead to the top of a big hill. One is steep and direct, and the other one is twice as long but less steep. How much more potential energy would you gain if you take the longer path? Now to answer this one here, let's just have a quick sketch here. We have here now this is the height for the hill that we're looking for, and this is the first track here, and the other one, it's less steep, as we can see here, the second case. Now, how much more potential energy would you gain if you take the longer path? In this case here, again, we are interested in the initial position and the final position. We are not interested in the path itself. So in this case, the potential energy you gained from if you take path 2 is the same as the potential energy you gain if you take path 1. So to answer this question, the answer is the same. No difference whatsoever. Now let's identify conservative and non-conservative forces. Let's start with conservative forces. Now, as we mentioned in the previous example, this one here, the work done doesn't depend on the path. So this is the definition of conservative forces. If the work done by force on a particle depends only on the initial, this is why initial here, and the final positions, in this case, this is called conservative force. Or another definition, if you start from y initial, go to y final and back to y initial, and the work in this case equal to 0, the force in this case as conservative force. Example for conservative forces: gravitational force is conservative, spring force is conservative force. On the other hand, a non-conservative force, if the work depends on the path itself, in this case the force is called non-conservative force. Now if you have position A and position B, in this case, if we take this path here and calculate the work, and take another path like this one here, and you calculate the work, you find out that the work done if you take this path here is the same as the work done if you take this path here, then force in this case conservative force. But if the work you calculated from path, let's name it 1, is different than the work done taken in if you take path 2, in this case you call this non-conservative force. Example for non-conservative force: friction, air resistance, etc. Now, if the force is a varying conservative force, then the relationship between the force and its potential energy can be written as this. So F in this case equal to minus the first derivative of the potential energy with respect to x. Example: the potential energy for one-dimensional conservative force is given by this relation here, where x in meters and u in joules. Find the force on an object at x equal to 2. In this case here, u of x equal to x squared plus 1. And in this case here, f of x is the minus first derivative of u with respect to x at x equal to 2, as required in the example here, which equal to minus 2x. If you derive this one at x equal to 2, in this case f of x equal to minus 4 newtons. That's it. This is the end of work and energy part 1.